V, add them up and transform, that is T of V plus W, it will be TV plus TW, right? And similarly, if you take a vector, scale, and then transform, it's as good as transforming and scaling, right? So alpha times V would be alpha times transformation of V. This is true for all VW in V. I think I should have used, let me use U instead of. Okay, so it looks like there is some it says microphone is not turned on. So can you not hear now? Now? Hello?
You're audible, sir.
Audible? Okay. Fine. So, so this is about linear transformations. So a specific type of linear transformation is basically matrix, right? So you use matrix to transform one vector to the other. So for example, you can transform a vector in Rn to a vector in Rm, right? This is a typical matrix based transformations, and it's obviously linear, right? So this is also linear. Okay, linear. Okay, so now, so why do you need to study matrix-based transformations? Because in many problems, you want to solve some simultaneous equations, right? For example, Ax equal to B, right? If you want to solve such equations, you need to understand what kind of, what is the effect of A on the vectors, and how do you recover X from this equation, right? Towards that, we ask this fundamental question of invertibility of a matrix. Right. So, what are the conditions that you need for invertibility? That was the next thing, right? So, A inverse. Well, we showed that A inverse does not exist if there exists X not equal to 0, such that Ax equal to 0, right? So, if this happens, then A inverse does not exist. But the opposite is not guaranteed, okay? So if Ax is not equal to 0 for every X not equal to 0, doesn't mean that A inverse always exists. So now let's look at the other part of this. Okay, among other things, we also looked at certain transformations, right? So how do you make, supposing, let's say I can transform A, suppose you have Ax equal to B, but A I can write it as U lambda U transpose, right? Some special transformation, then I can solve these equations pretty easily, right? You don't need to compute inverses, but you have to do some matrix multiplication, which is very easy to implement, right? Especially we started out with diagonals, right? So now, of course, this, for example, if I have a lower triangular matrix, let's say A11, 0, 0, 0. This is A12, A21, A22, and then 0, 0, 0, and so on. This is ANN, right? This is called a lower triangular matrix, right? For obvious reason. So now, if I give you a lower triangular matrix, how do you solve this set of linear equations? Ax equal to B. Very easy, right? So if you take the first row here and multiply with x, what do you get? Huh? So the only non-zero term is A11, right? So A11 gets multiplied by the first component of x, let's say x1. So we get A11 x1 equal to the first component of B, which is B1. So from which you can easily calculate x1, right? Done. So what about the second equation? So you get A21 x1 plus A22 x2 equal to B2. How do you solve for x2? Pretty easy, right? B2 minus A22 B1 divided by A11, that is your x1 from the previous equation. So this will give you x2 and so on, right? So pretty easy, right? If you have such a equation. Now, essentially, solving these equations boils down to somehow turning this complicated matrices into some simpler matrices, right? That's why transforming a matrix into simpler matrix is something that we are very much interested in. So let's go back to A inverse and let's look at one small aspect of A inverse. So suppose I have, it's a mapping, right, from Rn to Rn, let's say. Uh, Rn to Rn. Because if you consider Rn to Rm, there is no guarantee that you will have an inverse if m is not equal to n. Okay, so now we saw one situation where a single point here should not be mapped by two or more points in the domain of your matrix, right? A, right? So now the other thing that should happen is that is called 1 1, right? So you need 1 1. Onto is what? It should be covered, right? The entire the range space should be equal to Rn. So what do you mean by that? What do you mean by that? You take any point in this, in the range, right? Any vector. There should be a vector here that gets mapped to this vector, right? I'm not saying it should be unique, but there should be at least one vector that gets mapped to this vector, right? So let's write that formally, right? So for any x in Rn, okay, let me write y in Rn, there exists an x in Rn, okay, such that a x equal to y, right? Is that fine? This is should be the case. So what is this y? So this y should be here for every y in Rn in the range of your matrix. There should exist an x here, for example, this that gets mapped to this particular thing, right? That guarantees that the entire range space is covered, right? Entire Rn is covered as a range of A. So what do you mean by this? Let's look at what is the implication, right? So I can write this A matrix as column vectors, right? So A1 is the first column, A2 is the second column, An is the last column, right? N cross n. I'll multiply it by x1, x2, and so on, xn. That's equal to y, right? So the moment you see such kind of a matrix multiplication, right? Matrix multiplied by a vector. How can I write this? Is there any other way of writing the same thing? We saw that, right? What is that? A matrix multiplied by a vector. So how do I write that? Yes. How do I write that? Huh? Huh? What modification? Sorry. No, sorry, I didn't get. Individual column multiplications. Multiplication with what? See, essentially, what happens is, in this case, this x1 gets multiplied by this first column, right? This x2 gets multiplied with the second column. Do you agree? I mean, x2 cannot get multiplied with first column or the third column and so on. And so on, this xn gets multiplied by the last column, right? So all that you are doing is you are taking the first column of the matrix A, scaling it by x1, second column of A, scale it by x2 and so on, and then add all of them. That will give me the product Ax, right? So how do I write this? This is basically summation I equal to 1 to n xi, this is a scalar, multiplied by this ai, right? So this is what we get is equal to, I should get a vector y. So when is this possible? Can somebody tell me when this is possible? This should be true for any y in Rn, right? So I should be able to find x, that means xi's, such that if I use xi to combine the vectors ai, I should be able to get a vector y. When is this possible? Go back to the previous classes, right? So what is the definition? Huh? It's too much to ask for, right? If you say basis and all that. So y should be in the, so basically you take any y in Rn, that should be in the span of the column vectors, right? Do you agree? So in other words, span of A1 through AN should be equal to Rn. This is all it requires. Okay. But as a byproduct, what do we get? As a byproduct of this, you have n vectors of size n, the span of that is Rn, the dimension of that is also n, and we also showed that they have to be linearly independent previously, right? Do you remember that? It has to be linearly independent because ax should not, au should not be equal to av for all u not equal to v, right? So in that case, so there should not exist a vector x not equal to 0 such that ax equal to 0. That means they have to be linearly independent. So putting everything together, what do we get? A inverse exists if the columns of A form a are linearly independent and should span the entire space. What is that called? Basis of Rn. Right? In other words, the column should be linearly independent and it should span the entire vector space. Right? So what is the rank of a matrix? Can somebody tell me? Huh? Right? So that is called the rank of a matrix as of now. Okay, so it turns out that the number of linearly independent columns is also equal to the number of linearly independent rows, which is equal to the rank. Okay, is this clear? Any questions? So I'll pause for a minute and then we'll move on. I want you guys to digest these things. Have you studied these things elsewhere? If yes, then I will probably accelerate. Yes or no? How many of you think that you already knew what I'm speaking? Okay, one, yes. Anyone else? Huh? No? Okay, so let's move on. So this is about the inverse, right? So we have one result about inverse. Now the question is, how do you find the inverse? And how do you transform matrices in such a way that you get simpler matrices like diagonal or upper triangular and so on, so that I can solve these equations pretty easily, right? Those are the questions that we should answer. Before that, what we will do today is, at least some part of this class,